Intro to 1's and 2's complements for the digital computer. In this tutorial, we will describe how complements play a vital role in digital computers. In digital computers, complements are used to simplify the subtraction operation. For the binary system, there are two types of complements: 1's complements and 2's complements. So why do we need complements for the digital computer? To answer that question, I went out and found an article written by Greg Perry. Greg is responsible for writing several books, and a couple of the books I'm very familiar with. One book is Beginning Programming in 24 Hours, Sam's Teach Yourself, 4th edition. Greg, he wrote an article about binary arithmetic. And in the passage, at the start of the passage, he mentions that at their lowest level, computers cannot subtract, multiply, or divide. Neither can calculators. The world's largest and fastest supercomputer can only add. That's it. It performs the addition at the bit level. Binary arithmetic is the only means by which any electronic digital computing machine can perform arithmetic. And there you have it. So let us show an example. So if we take a number, say for example, we take the value 10, and we subtract 6 from 10, we will get the value 4. And that's how we see it as humans. But inside computers, they only understand 0's and 1's. So in this example, we can pretty much just convert, like for example, we'll see that we have the value 10. This is being converted to binary here. So the binary representation for the value 10 is 0, 0, 0, 0, 1, 0, 1, 0. And we want to subtract the value 6. So we take the value 6 and convert it to binary. And we have the value 0, 0, 0, 0, 0, 1, 1, 0. And what we're going to do, we're going to actually perform binary arithmetic. Okay, so what we do is to start off is we look at the first position here. We say, okay, 0, subtract 0, we will get the value 0. And we have the next column, we have 1, subtract 1, and we will get a value of 0. And we have a value of 0 attempting to subtract 1. But what we need to do, we need to borrow. So we'll take the borrowing from the previous column. So we'll scratch this 1 here. That becomes 0. And when we borrow, we're borrowing a 2. So we get rid of this 0. So 2 subtract 1, that's 1. And now the rest is 0 subtract 0. All of these will produce the value 0. And what we have here is a representation of the value 4 in binary. Okay, so let's go next. We mentioned previously that the digital computer cannot subtract. It can only add. That's it. So what if we are able to produce the complement of the value 6 from the previous problem? Well, the previous problem is what we have here. We had the value 10, subtract 6, and we will produce the value 4. So if we rewrite this equation, if you notice, humans, we're looking at subtraction, we're looking at this operation and say, okay, we want to subtract. But computers, they have to use addition. And in order to use this, we are going to have to produce the 2's complement of the value 6 and add it to 10 to produce the value 4. This is what happens with the digital computer. So let's look at the previous problem. We have 10 subtract 6 will produce the value 4. So we mentioned that the value 10 converted to binary, we produce a value 00001010, and we want to subtract the value 6, which is producing binary value 00000110, and of course that's going to produce the value 4, which is the value 00000100. So what we want to do, we know that the digital computer cannot perform this subtraction operation. So what we want to do is we will have to produce the 2's complement of this value here. So let us compute the 2's complement of the binary value 6. So step 1, convert the binary value 6 to its 1's complement form. Well, what is 1's complement form? So what is 1's complement form is this is done by converting all zeros to 1's and all 1's to zeros. So let's write out the binary value 6. We'll say we have 0, 0, 0, 0, 0, 1, 1, 0. And to produce this value to 1's complement, it's just a matter of converting each value to its opposite. And so we will start this process like this. So we have the value 0. We said that if it's a 0, you convert it to 1. We have the value 1, and if the opposite of 1 would be 0. So we have a 1, it becomes 0. We have a 0, it becomes 1. We have another 0, it becomes 1. We have another 0, it becomes 1. Another 0, it becomes 1. And we have another 0, it becomes 1. This is the 1's complement representation of the binary value 6. So that's step 1. So next what we do is step 2. Convert the 1's complement to 2's complements. And this is done by adding a 1 to the 1's complement. So we already converted the binary value 6 to 1's complement. We came up with the value 1, 1, 1, 1, 1, 0, 0, 1. And so to convert that to 2's complement, we add the value of 1 to the entire value. And what we are going to produce here is just do basic binary arithmetic here. So we have 1. It's good to do this to see where you are. So what I do is, so I know that I'm dealing with a binary number system. And so this 0 represents 0. It just helped me keep track of where I'm at. 1 is a 1. And so I got to represent the number 2 has to be this 0. This whole entire parentheses here is a 1's carry. And so this 1 here would represent a 3. So when I add 1 and 1, this is really the value 2 but we're dealing with binary. So 2 is represented by the value 0 here. So I put a 0 here. And then I carry the 1 because we're dealing with the carry here. And so 1 and 0 is 1. And then we bring down everything else. So we have 0, we have 1, we have 1, 1, 1, and 1. And so what we have here is the 2's complement of the binary value 6. So what I did at the bottom here, we started out originally with the value 10, subtract 6, and we produced the value 4. And then we said that, computers do not understand subtraction, they only understand addition. So why not say we have 10 plus the 2's complement of the value 6. We should still get the value 4. And so what we have here, we have the value 10 converted to binary. And this time, instead of subtracting the binary representation of the value 6, we're going to move its 2's complement here. So let's move that value there. So we have 1, 1, 1, 1, 1, 0, 1, 0. And this time, instead of subtracting, we're going to add. So we have 0 plus 0 is 0. And we have 1 plus 1 is 2. But we said up here that the value 2 is represented by the value 0 in binary. So we put a 0 here and we do a carry. So we add everything in this column, and that's a value 1 goes here. And then we add a 1 and 1 produces a 0. And then we carry. We have produce a 0 and a carry. We produce a 0 and a carry. We produce a 0 and a carry. And this produces a 0 and that carry. But the carry, we only care about the 8 bits. This doesn't really matter there. And what we have is the value 4 in binary. And this is what we wanted to show. This puts us in a position for my next tutorial where we describe binary logic. I hope this tutorial was helpful. Feel free to join us here at the Computing Sector. There will be more videos and tutorials coming soon. Do not forget to click the subscribe button. I look forward to seeing you soon. Thanks.